live, and it's a great pleasure to welcome in today's seminar Jeronimo Bezerra, a long-time collaborator. We have common research roots around software-defined networking, open flow, P4, uh, uh, and this internet exchange point landscape that is fascinating. I was seeing this week, maybe Jeronimo, you saw it, that the Brazilian internet exchange points have reached top aggregated capacity over surpassing Amsterdam, Frankfurt, and many other big IXPs, internet exchange points. So just to get some news into today's seminar. Today's seminar also, as I was talking to Jeronimo, it's also a special day. We are running here in the Faculty of Electrical Engineering, our second year workshop of this Smartness Engineering Research Center, which is a 10-year initiative co-funded by FAPESP and Ericsson. And we have collectively more than 50 researchers, students, and Jeronimo. The topic that you will be talking about is on spot, so that we can collaborate back again soon, hopefully. So it will be great to catch up with you today. I thank you for your time. I know you are not 100%. I'm not either. It's hard times. It was a hectic week. I'm also losing my voice. So without further delays, thank you. And let's plan for around 40 minutes, so then we can have around 10-15 minutes of conversation.
Well, thank you, Dr. Christian. Can you hear me okay? You
Yes,
see my
yes.
screen? Okay, perfect. Good afternoon, everyone. It's a pleasure to be here. I think the scope of the presentation, as Dr. Christian was talking about, is very aligned to the scope of work of the course, which is talking about state of art of computer science. In my case, I'm going to be talking about state of art of computers network. And the idea is to talk a little bit about what was done in the last 15 years, what has been done in the last 15 years to support this new use case that I'm going to show now that has needs for real time. So the scope of the presentation is network innovations to support real-time astronomy applications. And again, my name is Jeronimo Bezerra from Florida International University. So this is the outline, standard outline. I want to introduce some concepts first, like what is a research and education network, talk a little bit about the Vera Rubin Observatory, which is our science driver, the use case for this talk, and everything that was done at MLight, which is the network that I represent in terms of achieving the bandwidth, achieving the control, achieving the quality, and achieving dynamic closed loop orchestration. So for those who never heard of research and education networks, basically those RNEs, they create this networking fabric that connects all the researchers, scientists, and scientific instruments across the globe so they can collaborate at scale. So you can think as a parallel internet that is built to enable collaboration. It could operate at multiple levels. So a university campus is an RNE. We have city levels, we have regional, national, international. AMLIGHT is an international research and education network. They are supported by governments, institutions, research institutions, universities, and obviously funding agencies. So the main characteristic of a research and education network is to provide plenty of bandwidth. So the idea is that in the moment that you want to do some research that requires network bandwidth connectivity, that would be there for you. There will be no restricted policy. Everything is open, and it's supported by advanced services that the research and education networks also have. So those examples, some small examples, the Unicamp is connected to the research and education network of the state of São Paulo. There's called RedNasp, is funded by FAPESP. The Brazilian institutions are connected by RNP, that is funded by the Brazilian government and connect all the research and education networks in the country. We also have here in the US, And we have the regionals that cover the whole state, as you can see in the picture. And you also have the national backbones, like Internet 2, which is the dashed white line. And we also have YesNet. And when you start connecting one to another, you have this fabric. This is the node representation that goes back from 2017, but that's back then was called the GLIF, the Global Facility. And then you see how all the research and education networks are connected one another in a way that you have global collaboration. So someone in the state of São Paulo can easily send traffic and get traffic to Japan, Australia, Africa, and Europe. All of this is supported by collaboration, and there's no charge for you to participate of this. There's a charge to build this, but for the researchers, all those links are available for free. Our use case, right? So it doesn't make sense just to build a network to build a network. You have to have a use case. In our case here for this talk, I'm going to be focusing on this one that's called the Vera Rubin Observatory. Vera Rubin is a large aperture, wide field, ground-based optical telescope. It's under activation. It's being built in the last 10 years, and finally this year, after some delays with COVID, is going to go full production. It's based in northern Chile. It's an 8.4-meter telescope. It produces 13 gigabyte of data with this camera every 27 seconds. And the data, the picture and the metadata that is created in Chile has to be sent to the US within 7 seconds. So that's where the majority of the strict of the SLA, the conditions are, is the data has to be sent from Chile to California in less than 7 seconds, every 27 seconds. So the data could be available to the observatory community in less than 60 seconds. As you can see, there's plenty of challenge of building a network like this. So the first one, the most clear one, is since every data today in the internet is transmitted using TCP, there is a long round trip time here that for the data to go from Chile to Slack, there's more than 200 milliseconds. And any packet loss that goes more than 0.0001%, it's going to affect these 7 seconds. So meaning that if there's one packet loss every 10,000, forget it, we won't be able to achieve our goal in less than 7 seconds. So these are some pictures. This is the mountain when it was flattened back in, I think it was 2014, 2015, maybe 2013. So Chile is usually selected to be the house of those telescopes because the air is very clear, it's very dry, the weather is very good, and there's not a lot of light pollution. So they picked a mountain, they flattened the mountain, as you can see, and then through time, they sent these 8 meters wide lenses. They sent the camera. Look at, there's a person for comparison. This is a 13 gigapixel camera. Um, and this is the way it is today. So you have the main camera on the left side and the auxiliary camera on the right side. And this is an observation at night because there's no light pollution or there's minimal light pollution. You get to see the whole Milky Way from the perspective of the southern hemisphere. So the way how Vera Rubin works is we take a picture from Cerro Pachón in northern Chile, and then there are several networks in the path. There is the Research and Education Network in Chile called RIUNA. There's MLIGHT, which is a consortium of several research and education networks that operate in the state level and the international level, national level. So the most common ones are RedNASPA for and RNP for the Brazilians, but also there's one in Florida, one in the US called Internet 2. There's FIU, Red Clara, that operates in Latin America. There is the Energy Science Network in the US, and there's the SLAC, which is the institution that hosts the data archive. So it's composed, it has a primary path of 100 gig, fully dedicated with protected path like achieving 40 gigs. A total primary path goes 21,000 kilometers of fibers, 13,000 miles, 50 different routes that can be taken from northern Chile to California. We have dark fiber, DWM, Ethernet, MPLS, SDN, all technology that you can possibly imagine are being used here. A lot of monitoring tools, a lot of monitoring nodes, and one of the first criteria is the SLA. The SLA for packet loss. Remember when I said back that one every 10,000 packets being lost is damaging. What they are asking is for one every billion packets. So the criteria for packet loss is very, very strict. It's even hard to measure this. And this is how the telescope is going to operate in loops of 27 seconds. So there's the blue line represent the data transfer going all the way to 40 gig plus. It's not 5 seconds anymore, it's now 7 seconds. So there's a time that the picture is being taken, processed, and then we transfer. Then we take a picture and then we transfer. Then we take a picture. This goes all night long as the sky is clear and it's night, we're going to be doing this. And the challenge for us is picture that there is a condition that leads to a packet loss somewhere in between two data transfers, right? So how fast do you think a network engineer in the middle of the night can react, can wake up, get a coffee, connect it to the router, and troubleshoot the network to fix a problem to make sure that it won't impact the next data transfer window in 20 seconds? That's pretty much none, right? And even the following ones, probably maybe all night long. In some cases, we won't be able to react because we don't know where the problem is. Sometimes troubleshooting across multiple domains takes forever. So this is the main driver for us is how we automate the faulty, like soft packet loss detection in our network. So some of the motivations, as I mentioned before, the round trip time from Chile to Brazil, Florida, and Atlanta, it's quite long. And any packet loss is already bad. And we now have science drivers like the Vera Rubin here that expect a better network performance. They pay for network performance, and in fact, they demand better measurement. So different from the traditional science driver that uses whatever is available, Vera Rubin pays to get the best because their science driver, their workflow is very strict. The data has to be available to the community in 60 seconds. So there's not a lot of space for mistakes here. And as part of the service level agreement, they have two attributes that are called mean time between failures and mean time to recover, which are very strict. That we can only have one total failure per year, and that failure cannot be longer than 10 minutes. I think it's in fact it's 1 minute, but I'm just being nice and saying 10 minutes. But that you can see here that 10 minutes per year, it's completely surreal. So it's hard for you to do this with traditional network operation tools and software and devices, right? So you have to customize the network to support this. And that's what we did at MLight. We decided to go with a solution that we built from zero. So we had to tackle a few challenges. Remember, we're back in 2009, 2011, when all the conversation started. So first, we had to find bandwidth in Chile and Brazil. There was not a lot of options. Most of the cables were old. We had to find a new networking stack to make sure that we could react to those faults, that we could have visibility, that we could achieve the performance, we can evaluate the performance, and that we could do some sort of traffic engineering that goes maybe under 5 seconds. So let's start with the first one, right? So the first one was, well, this is a map from 2010. There were only two main cables that were really available for the community to use in terms and get bandwidth. For those who never heard, everything on the internet that crosses continents, sometimes countries, go through optical fiber, and sometimes those fibers are in the bottom of the ocean. So those are two fiber cable systems that are in the bottom of the ocean connecting all those countries. So one was called SAC, that belonged to a company called Sparkle, and the same one that was called belonged to a company called Telxius. Those cables were already old in 2010. They were at least 10 years old. They were almost at 40% of the lifespan. And they didn't have any support for 100 gig, right? The maximum bandwidth that you could get on those cables were 10 gig. And everything was you pay per bandwidth. It was like a contract, was called like a lease service. It's just like in your house. You buy 300 megabits for your house. You buy 100 gig, and if you want more than that, you have to sign a new contract, and it is a complex process. So FIU, in partnership with FOPESP, had the idea. Okay, so how can we expand the bandwidth here? How can we play with this environment? So there was a project that was funded by the National Science Foundation in the US called Project OpenWave. And open wave was very bold and revolutionary because it wanted to inquire, like it wanted to ask the submarine carriers to provide us access to the fiber itself, like through the possibility of owning an optical channel. So this was never heard of before. Nobody was doing this before, especially in a submarine system that is a very structured environment. So we wanted to own a part of the optical spectrum and decide and choose how we're going to light that spectrum, meaning that I could put whatever transponder I wanted. So this was accomplished in 2012. That was called back then alien wave, is when you put an optical wave lit by a different technology that not the same technology using in the submarine system. So it was pretty challenging. We had to do for those who are from the optical environment, we had to do a lot of regeneration. We had to do a lot of customization. It was at almost 10,000 kilometer fiber span, which had to be regenerated in Rio de Janeiro, between Santos, Rio de Janeiro, Rio de Janeiro and Fortaleza, Fortaleza and St. Croix and Miami, right? But the idea is that we want to make sure that we could do this in a safe way, because we didn't want to kill the other channels on the same cable. Obviously, this is a commercial production cable. And we also didn't know how we're going to operate this, right? Nobody knew back then. So through this collaboration with Sparkle was very generous, very open to the participation. We deployed the first coherent technology. The coherent technology means that part of the spectrum is also supported by digital signal processors, or DSPs, right? So that you have an electronic component, is not anymore just optical. So we had the coherent technology for an alien wave, and then after 2014, after learning all of this, now this cable has 100 gigs. So there's 400 gig for sale if you want. Maybe not an alien wave, but we're now limited to 10 gigs. So we kind of address that limitation. And with the experience of supporting our own channels and submarine cable systems, we then went after Angola Cables, which is a carrier that connects Brazil to the US to Africa. And we acquired optical spectrum on their cables, the Monet submarine cable that goes from the US to Brazil, and SAX cable that goes from Brazil to Africa, to Angola. So this is what we did. Like after 2016, after all the carriers are getting more comfortable with the idea of you having access to an optical asset, we got spectrum Monet, we got spectrum SAX, we got spectrum within Florida, we got spectrum Antenna, which is a cable that connects us, São Paulo to Argentina, and we lit all of this with CN Wave server AIs. So that means that we own the transponders, and we, at any point we needed more bandwidth, we just replace the transponders, and we don't need to sign a new agreement with any carrier. So today we have 39 100 gig links spread in the network. We're activating 800 gig any day now between Brazil and the US. And in total, we'll have 4.9 terabits per second of total capacity by the end of this year. And those are all the sites where we were present. So this is our network today. Everything that is green is optical spectrum. Everything that is white is still lease capacity. And everything that is pink is a collaboration with our partners. So, okay, we handled the bandwidth. We found different ways to get from Chile and Brazil to the US. Now we need to talk about control, right? So this is what we did in terms of orchestration. We added dynamic circuits. In 2014, we moved everything from legacy spanning tree to software-defined networking, SDN. It was one of the first international networks, and we still operate as an SDN to the date. In 2019, we added a P4 programmable switches. In 2020, we added support for in-band network telemetry, which I'm going to go into details later. And by the end of this year, if everything goes well, we're going to have a sub-second dynamic traffic engineering solution that will accommodate those challenges that I presented at the beginning. So for those, I think everyone knows what SDN is at this point, but SDN is basically decoupling decision-making from forwarding actions, right? So you take all the intelligence out of the equipment, put that in a controller, a centralized controller, and all the devices just take order from the controller. The controller has a topological view that includes all devices, all links. So the SDN controller is the entity that creates the services. So we built this, and this is the architecture that was designed by the IETF, the Internet Engineering Task Force, RFC 7626, is that you have an application plane, you have a control plane, you have a management plane, and a data plane. The problem for us is that back in 2014, there was a software that does all the software planes, right? The application control and management. Everything was coupled together, but it was still an SDN controller. And the data plane, it was a mix of whatever vendor was available, right? Because we had Brocade, we had Corsa, we had Dell, we had Junipers, in each vendor providing a different support to SDN and to OpenFlow. So it was hard to have a very reliable and maybe scalable, flexible solution because every device and the data plane behaved in a different way, right? And the software was just one software that controls everything. So this made it complex to expand. We still had fiber cuts and device outages being like repaired by the software, but anything else in terms of traffic engineering and optimization was seriously limited. But it was still very positive. These are some numbers, this is the publication in case you want to read more. This is before and after deploying SDN. Some of the things that used to take 5 days, 12 days in the legacy world to cross multiple domains now are taking less than 5 minutes, right? So it showed right away that the software could be responsible for provisioning new services, even though we are crossing multiple different technologies and multiple domains. So this was a great progress. That was amazing. That is us putting our foot in the water of SDN, and everyone start like using this kind of reference, like this kind of paper to show, look, SDN has a purpose here. And those are some of the consequences, right? A lot of publications came out of these experience because we start creating tools, we start testing devices, we start testing applications. So there were several publications that came out of this implementation. But then in 2021, we realized, look, this environment is still, as I was saying, there was a one software for all the planes, and that makes it very hard for you to expand. So we decided to make it more interesting. We create new planes. So we call now the intelligence plane that is responsible for learning and profiling the network and understanding the network state. We create this documentation plane that is now everything goes through documentation first to then become a configuration. And the management plane, it was a switch from using legacy technology like SNMP and then OpenFlow counters to use the P4 capabilities, in this case, in-band network telemetry. So this is how our stack is supposed to be at the end, right? So you have a data plane, and the data plane at the bottom in green, you see two boxes in purple. One for the optical layer. Remember I talked about transponders, that I talked about optical spectrum? We have to manage those devices now. And those devices export telemetry to our management plane, just like our packet layer, our SDN switches that use P4 now with OpenFlow 1.3. Then we have this management plane here in the middle that collects all sorts of data from all sorts of sources and just creates summaries. And those summaries we call the network state. The network state is sent to the intelligence plane that does a profiling, make sure that looking at the documentations and the policies, it is doing what the network is behaving the way it's supposed to behave. And if there's any recommendation, this intelligence plane will send instructions or intends to the control plane for the control plane to send instructions to the devices. So you can see this red circle here where you have this closed loop orchestration that could be used for healing the network, but also for optimizing the network, right? And then on top, you have our NOC that approves the policies and our network monitoring system that trigger alarms, open tickets, and all of that. So a little bit of exploration about each one of those planes. The main one for us was a control plane, because in the end, everything is about control, right? So we decided that we needed to build our own software. The tools are available in the market were good, but they were not customized for our needs. We had Vera Rubin's SLA that were very restricted. We had telemetry that was, we are the only ones that use INT in production. The Vera Rubin had very complex path findings. As I mentioned before, there's more than 50 ways to get from Chile to Slack. So how do we decide what is the best route to get from point A to point B, right? So this tool is in production, is being built by FIU and RedNasp and support from FAPESP. It started with FAPESP funded the State University of São Paulo back in 2017. And today is fully maintained by FIU and RedNasp. And this is the GitHub link. Is completely open source. If you're looking for be engaged in the SDN, I suggest that you take a look, and we're open to collaboration on that. Then just control without the proper hardware makes no sense, right? We had to get rid of all the blend of vendors that had different support towards one device that supports everything we wanted. And you probably heard Barefoot Tofino was released in 2016. 2020 was acquired by Intel. So the Tofino switches are switches that have the Tofino ASIC. They are very programmable using P4. So we decided to risk and go with that platform. It's very small switch, it's very power efficient, has high density of 100 and 400 gig ports, and it had the capability for us to do the INT, which is the in-band telemetry that we're looking for, right? And don't worry, INT comes next. But we also have to find what is the optical solution. So we chose to go with the Sienna Wave server that supports streaming for telemetry, which we're also going to use and talk about next. And it has an API that we can collect all the telemetry data and collect different data to do anticipation of faults, right? So this solution was amazing in the sense that before we used to have switches that were like maybe half meter long, right? It used to have like use maybe 3,000 watts of energy. And now we have those an inch and a half switch that consumes maybe 450 watts, right? And the same for the optical. The optical, we used to have the Sienna 6500, which was a huge platform. And now we have one rack unit, inch and a half tall device that uses very little power. So that was very efficient for us in terms of collocation, power, and maintenance. So, okay, we handled topic number 2. Let's go to network visibility, right? So it was not accurate and it was slow. So what does that mean, being slow, right? So we start doing an assessment, right? So what are the technologies available today, like SNMP, S-Flow, Juniper telemetry interface, and INT? And we start comparing them. And we saw that they complement each other. They don't replace one another, they complement. But for achieving the visibility, the sub-second or close to a second visibility we're looking for, only INT could give that information, right? So INT, it's great for troubleshooting short time events. It provides full visibility, but it has a cost for that, right? Something else that we notice is that even devices that have good telemetry using SNMP or open flow counters, sometimes there is a time delay between an event being detected on the data plane and that event being reported to the management plane, right? So if you have an SNMP counter, like a traffic coming into the interface and change the octets, that octet will only be available to an external tool like SNMP or open flow counter sometimes after 7 seconds, sometimes 20 seconds. So how can you do a real-time network operation if all the data is at least 20 seconds late, right? So you can't do real-time anymore. And on top, you're going to see the yellow line. The yellow line is the only SDN-only device here, which back then was a Corsa switch. All the other devices were traditional legacy solutions. So we had to go towards something that was clearly SDN based, and also a protocol that was better for real time, like streaming, which is the INT. So then we did another experiment. We start simulating microbursts. This is Renata's presentation from the Internet to Technology Exchange of a couple of years ago, where she created two traffic, right? Two streams of traffic. One continuous sending 20 gig and 15 bursts of 30 gigs, each burst during 200 milliseconds. And look at how the technologists reported that traffic. Only INT was able to count the spikes of microbursts, while the legacy technology like Juniper and SNMP were only capable of showing a flat line, the total counter for that. And this is everything here is 30 seconds. It's a very accurate, very small time interval. So you can't have a real-time decision-making solution if the data that you get is not reliable, right? So that again, it's another point for INT. So, okay, so what is INT that we talk so much, right? INT or in-band network telemetry is this solution that adds telemetry to every packet as a packet crosses every switch. So you have the node sending data to a destination node. Those nodes don't see anything, but every packet gets stacked with telemetry. And at the end border of the network, the telemetry is exported to the telemetry collector, and the user never sees a thing. This was a publication that we made as well. But when you have telemetry per packet, that means that you monitor every packet, right? And every packet is monitored at line rate and in real time. So that means that you have full visibility, but with great power comes great challenge and responsibilities, right? So it's a lot of data because every packet now triggers telemetry. So today we have around 10 million packets per second of telemetry, 96 terabytes of data per day, right? But with that data, we can monitor instantaneous bandwidth utilization. We can monitor instantaneous buffer utilization, something that most of the vendors don't support at all. We have per hop delay, and we have path tracing or proof of transit, right? So now we have everything that was happening to the switches, we know. We just have to start using that. So those are some of the graphs that show what you can do when you have full visibility. You can see the buffer utilization of a switch, like all the memories inside the switch, in a very like small time interval. And you can see on the left side, everything as is expected to behave. You see the buffer utilization is like 30 kilobytes. You see the delay per switch is 2 microseconds, but when you have a congestion, you see megabytes of data on the buffer, and you see milliseconds or 10 times more and delay caused by a single switch, right? So this is the kind of visibility that we can only do if you use a technology that exports data per packet. So this is now the management plane, right? So the management plane that we built, it was based on having an INT collector that gets all the data that was talking about, all the 10 million packets per second, a GNOI collector that gets telemetry from the optical layer, and all the standard S-Flow, SNMP, syslog, a monitor that we get, right? So we get all the data to then export that data to the intelligence plane later. So perfect, we have visibility. So now what about performance? How do we know that the network is behaving the way it's supposed to behave? So we built a traffic generator. So the traffic generator is this appliance, is a device that you buy. You can see some pictures here that the only purpose is to send traffic. And because everything is done in hardware, you can rely on those results, right? It's not a software solution, it's a hardware solution. And because the switch and the telemetry is also done by hardware, you can rely on the results, right? So we bought this traffic generator, and we built a software that connects all those entities that we talked before, the intelligence plane, the documentation plane, the control plane, and the traffic generator to automate tests in a very small interval. So we're testing the network every 30 minutes. So this solution is called BERT OD, as bit error rate test on demand. And basically it can find like loss, packet loss, as low as 10 to the power of -9, meaning one, maybe sometimes a million, sometimes 10 millions, all the way to a billion, right? And everything, again, leveraging what was built before. So you can see that there is a sequence, right? There's the SDN, the switch, then INT, now the testability of the network. So because all the components, again, are hardware based, we have very accurate results. So this shows a little bit of during the implementation phase, the left side of the red bar shows like how the network was behaving in terms of loss, in terms of jobs that we're not accounting because sometimes they're so small, like a one packet being lost per day, that they were not being captured, like detected by any system. But once we had the solution in place, we started highlighting those 1, 2 packets lost per day, and we started acting upon them. And the red line shows like one of the maintenance windows that we did to start replacing fibers or cleaning fibers, scoping fibers, right? And through time, we started making more changes and more cleaning and more fixing to the point that the network is much cleaner than it used to be, right? So this is a consequence of integrating visibility, telemetry control, and the packet generator. Perfect. So now we can trust the performance, but can we do anything dynamic with that? So this is when we build the intelligence plane, right? The intelligence plane gets all the data from all the other planes, like it gets the telemetry from the management, it gets the policies from the documentation, interacts with the control for topology, and profiles the network every 100 to 500 milliseconds. What does that mean? Is that it gets all the data that is available, compute all the data that is available, and tell us, well, the network is good or not, right? So that's profiling. So we're profiling the network in this interval. And then with that profiling, you identify who has, if there's a problem, where the problem might be, or what is the source of problem, in this case, if the problem is a flow. So, and by knowing this, the intelligence plane can submit instructions or intents to the control plane. So the control plane will then take an action, which could be steer traffic, move to another link. It could be a load balance of the services. It could be rate limit anomalies or even drop anomalies, right? So we're even now considering doing this for DDoS mitigation and other kinds of attacks. So this is a change of a mindset compared to the previous project, previous year. There's missing here. So the goal is to be prepared for sub-second traffic engineering. Remember that the goal was 5 seconds, but we learned that because of we profiled everything here, we know we can do this every second if necessary. So some examples of policies here. If you have a link that has bandwidth utilization of 80% or more, for more than 2 seconds, do something. Could be steer traffic, right? If you have 50% of queue occupancy for more than 2 seconds, do something, right? Load balance sources. Or if you have a link or a service of flow that keep changing path more than 5 times in 2 hours, it means that that link is bad or the link aggregation is not properly behaving. Something is happening, right? So then you can take an action, right? So you have this kind of granular policy now because you have the data. So we accomplished this, and the question is, well, has SDN, D4, INT, and optical spectrum combo combined, right, supported our goals? And as just give some context again, from Chile to Jacksonville, there's more than 25 possible routes just in this segment. It would be impossible for you to have this traffic engineering being done manually, right? So with this visibility, yes, this combination helped us to find the best path and make sure that there's a load balancing in our network. When we have this kind of SLA-driven packet loss intolerant application like Vera Rubin, if you have per packet telemetry, a sub-second profiling, yes, you're ready to react right away in case of a problem. And with the optical telemetry, we can anticipate failures. So because an optical failure doesn't necessarily happen as like a hard stop, it can get worse through time. You can anticipate when the network is going to be in the bad shape and maybe get the services out of that link before it happens. And with all of that automation now, our team has time more for like thinking of how to automate more routines, right? Or how to improve the code, not necessarily keep doing creating VLANs or changing VLANs or deciding which link has the proper amount of traffic. All of this can be done automatically. So this is what I wanted to cover. I see that we have a couple minutes. We have 20 minutes. We can have question Q&A now, or if you want to have more slides, and I can keep going. So I just wanted to have this as a checkpoint now.
Thank you, Jeronimo. I really love this stuff because we can see some of the original software-defined networking, the automation, the gains, the layering, the abstractions in production. This is what I tell my students that when they question, like they don't believe that something like in-band telemetry truly exists, and you are showing a use case. And I was going here through some of the questions of the students. You know, the students in this seminar class, they have homework that they need to do before the seminar starts. So, and the AI and machine learning is more than popular these days. It's overall present. You show the intelligence plane, of course, without good data, fine granular data like the in-band telemetry and the optical, everything. There is nothing you can do. Is there more? So questions are around what else can we expect from advances in artificial intelligence? What would be the next degree of automation? Can you share maybe some of the vision or steps ahead around this evolving application and real application of AI or evolved AI into network operations?
Oh, that's a good topic. Obviously, we're working with AI. We have people focus on AI. We are producing the data sets so we could have data sets to learn from, right? We're simulating events. We're documenting the existing, like a DDoS attacks. We always save all the files for learning, for running with the models that are being used by our team here. So we're producing data sets to support traffic engineering. One of the things that we got with INT was that there is a lot of data, right? There is so much telemetry that you can get from the switch that we never had access before at such a fast pace that the question is, well, what else can I get from that data that I never thought about, right? So we went with the basic ones, calculating instantaneous bandwidth utilization, buffer occupancy, but what else is there, right? So our partners in this project, ESNet, they have FPGAs and they are exploring the TCP IP layer and tracking like retransmission and tracking out of sequence and tracking one packet attacks. So there's a lot of possibilities with this amount of data that you can do it. It's just that you need people to think about it, right? But we understand or we believe that in the future AI, having access to this kind of data, we start having questions that we never thought about it and look for the answer and maybe find the answer in the data that we never thought would be possible, right? And then in the future, the idea is that you can automate more and more and more of those activities. So we only do the basic of the basic of the basic. All of this comes with it, a lot of investment, a lot of challenge, a lot of dedicated from the big team. But I'm gonna go on the limb and say, well, we're still doing the basics, right? We're still building the foundation for a new technology or new people to come and all. So let's think of this problem in a different way. And I think AI could be very good for that. So I think our main contribution to this field is we have several projects funded to just export data sets. So the machine learning community can having access to that data, come up with those questions and answers that we never thought about.
Great. Yeah. This topic, we were discussing this yesterday. Like if you put the AI component in your control loop and you remove the human and something goes wrong, right? The explainability part of the AI becomes critical. So why did you take that decision of rerouting or so? And this we are seeing in our community that scientific papers without an explainability section, they are not they are rejected, right? So there needs to be explainability behind the decisions. The AI black boxes are not something that a network operator would fully trust. So it will take a long time, right, to get into these other degrees of automation. Yeah.
Yeah,
Um,
that's true. One of the things that we are, when we build our workflow, the big picture is that for some more critical decisions, a person would have to approve, right? At some point, if you're if you learn something and you come with a very unusual approach for that, some human will have to review that and approve. So you can't be too loose, right? Cannot trust the system that much at any point. So yes, so that's the reason having good data, exploring data sets, doing our part to generate those real data sets. It's a contribution. That's what we want to do it. But we totally agree. Yeah, you cannot just trust blindly.
yeah, great. Yeah, data is the first key element. Let me now a question of my own. We were recently exploring with a partner here, a research project. It's a company that manufactures optical devices. The concept of network digital twin, and we managed to build a model based on telemetry data, so fine-tuned with telemetry data that was able to pinpoint faulty amplifiers even before they get into hard failure, so soft
Yeah.
failure type of. And this was beautiful when we were able to see the powerfulness of these advanced techniques of machine learning with real operator data. And then and it was the first time that we also saw some of our algorithms moving and making it all the way into products and operation. Do you see this concept? Have you this of the digital twins, of the optical digital twins, of having an instance that is a digital representation of the network, and that you can run some what if scenarios or other type of quality of transmission type of experiments on this digital version? Have you heard about this? Can you share your thoughts?
Yes, a lot more than I would like, to be honest. That's all people are talking about now. I came from two conferences, one called PTC, the Pacific Telecom Conference, which is all about submarine, and the Open Fiber Conference, which was all about fiber infrastructure and optical systems a couple weeks ago. And everyone is talking about using AI, building digital twins, and using trying to be proactive about detecting events, right? And not just that, but also use AI to help build the next generation, the 1.6 terabit interfaces and further than that. There's a lot of commotion also to start using the same infrastructure, the same way that you had access to the telemetry to identify a faulty component. People want to use that data to use the fiber as an instrument to detect environmental change, right? So there's people doing using fiber and the optical signal to detect mudslides, earthquakes, fire, traffic, potholes on the streets, fencing being cut. There's so many new uses for fibers, thanks to all the telemetry to AI that were never thought before. That create a huge new area, which is called environmental sensing or smart cables, this kind of thing. So yes, there's a lot of conversations. Digital twins is something very important in this concept. Uh, and when we thought that fiber was pretty much like a stale environment, it just went around and it's a whole new universe now. So yes, it's more active than ever, I would say.
Nice, 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 nice. Um, and now on another now a question for the younger engineers or researchers. If now this is the type of more personal question. So if you were now to go back to faculty and and start some topic, which one would you select? Which recommendation would you give? I was telling my students that I'm intrigued by the quantum communication possibilities. Honestly, the word is intrigued. I tried to learn. We had this seminar last week, and I have some students that helped me learn about this topic. Which one would you pick if you were to go back to school or enter back into some research track from now? What would you say?
So uh, yes, quantum is something that is very promising. I would not go back to quantum if I had the chance to go back myself. As the majority of people in IT and networking, we choose this career because we don't like development, right? Software development. And that was a mistake, right? We never thought that networking would be so much about software the way it is today, and I kind of ignored. So I would say, don't create this, you know, negative feeling towards software development because it's a lot more connected to networking than we ever thought. IT, it's even unquestionable, right? So we have Docker, you have images, containers, you have the whole context of virtualization. So there's a lot of automation that requires knowledge of software. But I would say that the main thing for me would be, don't skip the statistics classes because AI, machine learning, data science is all about statistics, right? And we always, when we're in school, we always think, why am I going to use this math for, right? I'm an IT guy. I like computers. I like networking. I'm never going to use this. I'm not going to be a researcher. You don't need to be a researcher to need AI or use AI today, right? And the whole background of statistics, if I could be back, I would, improve a lot more. So understanding the results, understanding research, interpreting results and data, it would be something. It is something that I strongly suggest everyone to be very careful and not to skip those.
That's a great concluding thought, because these days it's so easy to do this wipe coding and installing some framework and throwing everything and then just believing the output without further deep understanding on what is going behind. And this is a dangerous path, as you can see. And going back to software maths, there are core concepts around abstractions, simplicity, interfaces that are recurrent, that you see them then, of course, in different domains, in different setups, like you were showing the SDN at the end, software defined, builds up from these core ideas of modularity, abstractions, and all these have their roots in core maths and engineering practices like software development. So, great message, Jeronimo. Let me see if there is some question that I may have not seen live from our YouTube audience. No, just a big hands. And thank you. Let me see here in the Meet chat. No, the students are quiet today. and we can close. And thank you again for your time. Congrats for the great work, really inspiring. And as I said, I honestly mean that we need to catch up. We want to get our hands on your data sets. You know, in academia, these large data sets are totally meaningful for the type of research. And I think we have good opportunities for doing something meaningful together in the next years.
That's for sure. Yes. I'll be waiting for your contact.
Yes.
Thank you all for the opportunity. And I just want to highlight this. This is a huge teamwork, right? It's a huge effort. It's not just FIU, it has partners in Brazil, Chile, in the US, all the astronomy community. None of this would be possible without their approvals, because changing the approach and the mindset of going something that new is very bold. You have to really be open to the idea, because as any research, you could fail, right? And we can still fail. So this community and Emilite is amazing. The personnel involved and made this project so successful the way it is today. So, well, thank you for the opportunity to present here, and I'm always going to be available in case there's any questions or follow-ups. You have a great day.
Great. Have a great day. Acknowledging the true doers, all the efforts is always relevant, and you just did the right message of acknowledging all the efforts, all the teams. We don't have time to list them, but there are a lot of folks behind this, and you can find more in the links, right, and get in touch as needed. Again, thank you all. And next week we have another seminar schedule, so looking forward in 7 days minus 1 hour for another great seminar topic. Thank you. Take care.
Thank you. Bye-bye.